We're on to our next topic now, which is functions. And one of the things we need to do here is escape very quickly from the idea that a function must be a formula. Functions we need to be much more general than that. So we need to escape from the idea that we need a formula so that when you give me an input, I do some arithmetic and things and return to you an output. So we're escaping from that idea that we've had sort of drilled into us a lot doing high school mathematics and doing calculus. So let's get on with escaping from the idea of a function as a formula. So we're really used to thinking of functions as formulas or perhaps algorithms, especially if you've done some programming. In particular, they all have the form of give me an input number x, I do some arithmetic on it, or maybe use some lookup tables so I can compute sines and cosines and logarithms, and I put all of those things together doing arithmetic to give you a return value, which is going to be some number y. Now, one of the things we should realize very quickly, and indeed if you've done some programming you will have seen this, that we can define functions on objects that are not just numbers. So for example, I can define a perfectly good function which takes as its input a day of the week written in English, like Sunday, Monday, Tuesday, and return the first letter of that word, again written in English. So for example, I can draw its nice little diagram here if I move my head out of the way slightly. If I give as an input the word Sunday, then I return the letter S. Monday, I return letter M. Tuesday, T, Wednesday, W, and so forth. So I take as an input one of the days of the week and I return to you a letter as the output. So nothing numerical here, it's really just playing on letters and words. Now, once we start drawing diagrams like this, we realize we can define all sorts of things to be functions by drawing arrows backwards and forwards, but we should realize that the thing that we want to be a function has to be well defined. So in particular, if I tell you, as I did here, that I can take as an input any day of the week, then I have to be able to process any day of the week that you give me and return you an output. So we have to have an output for any given legal input. At the same time, I also need that if I evaluate the function, say, at a particular input, say Monday, and then I come back 3 hours later and I evaluate the function again on Monday, that I get the same output. So that is, one input value only ever gives one output value. So we shouldn't get two outputs for the same input. So let's go a little bit further thinking about things as sets and think a little bit more about what we mean here by well-defined. So to summarize, we summarize that previous function instead of as an algorithm, but actually as some sort of lookup table. If you give me the input Sunday, I return S. If you give me Monday, I give you M. Tuesday, T, Wednesday, W, and so forth. So really what we have here is a set of ordered pairs. And indeed, we have a set of ordered pairs coming from, as an input, the days of the week, output, the first letter of the words. So we really have something here that smells a bit like a relation, because a relation is just a subset of the Cartesian product. Now, more generally with our function, it's going to take inputs from some set A and give you outputs in a set B. And so we can write, just as we did up here, write this as a subset of A times B, so giving us a type of relation. Now, but we still want this thing to be well defined, so not every subset of A times B is going to give us a function. Okay, so we definitely want things that are still well defined. If I get my pen to work here, it's not playing nicely. Okay, so we need an extra few conditions here. So first thing is, every input from A has to have an output in B. I tell you, hey, I can take anything from A and do stuff to it to give you a result, then every input in A has to have some output in B. So to write that symbolically, for all A and A, there exists B and B, so that AB is in my function, in this subset of the Cartesian product. Additionally, we know that if we evaluate the function on a given input, then come back later and evaluate again on that same input, we'd better get the same output. So exactly one output for a given input. So again, symbolically, if I evaluate at A to get B1, and I evaluate at A to get B2, then I'd better have that those two outputs are actually the same output. So B1 equals B2. Now, we can put all of this together to make a nice formal definition, which is what we'll do now. So let A and B be non-empty sets. It doesn't really make sense to define functions on empty sets, so we don't do that. So let A and B be non-empty sets. Well, a function from A to B is a non-empty subset of A times B. So we're building on top of our definitions of sets and relations in order to define a function without anything to do with formulas or arithmetic. Okay? So we take it to be a subset of A times B with extra conditions. And those extra conditions are that for every A in A, there exists a B in B, so that AB is in F. Namely, any legal input, there is some output in my function. Additionally, if I input A and I get output B, and then I input A again and I get output C, then I'd better have that those two outputs are actually the same. So it's an extra condition that I need. Now, in this context, we talk about the input set as being the domain of the function and the output set being its codomain. Additionally, to have slightly more comfortable notation than this ordered pair notation, if A and B are in F, then we just write this notation we're used to doing, namely F of A equals B. So that acting F on A gives us B, and we sometimes will say that B is the image of A. Finally, we define the range of a function F to be everything in B that is the output of some element of A. So that is B in B, so that you can find something in A that maps to B. Now, note that range is always a subset of the codomain, and the reason we distinguish these things is sometimes computing the range, in fact, typically computing the range exactly is actually quite a difficult task, whereas knowing that all of my functions end up in a given set, that's actually quite easy. So we distinguish between range and codomain because range is typically quite difficult to compute, but codomain is typically quite easy. And we don't often need the range exactly. Okay? So we make that distinction. So let's look at an example and a non-example now. So we've got two subsets of z times z. So these are both relations. We're going to see which one's a function. So f is the relation or the set of ordered pairs x comma y so that they satisfy 3x plus 2y is 0. And g is very, very similar, except it's 3x plus y equals 0. Now, it turns out that the function f is not a function, so I was wrong to say the function f. The set f is not a function because it's not defined everywhere in its domain. That is, there are input values like x equals 1 so that we can't find an output. For x equals 1, there's no integer y so that 3x plus 2y equals 0 because we'd actually need, well, what we'd need 2y equals minus 3, so y is equal to minus 3 over 2. And that's not an integer. Okay? So given this input, there's no possible output. So it's not a function. On the other hand, the set G is a function, and we can again check, no matter which input x we get, we can pick an output, namely y equals minus 3x, and then that pair x comma y satisfies 3x plus y equals 0, and so is in our set. Okay? So every input has a legal output. And really all we're doing here is expressing the fact that this is g of x is minus 3x. Okay? Further, we can check this input, that a given input only has a single output by saying, right, well, if xy is in G and xz is in G, that is, if we put in x and we get y, and later on we come back and we put in x and we get z, then we need to verify that y equals z, that those two outputs are actually the same. And we see that, well, 3x plus y have to satisfy that, 3x plus z has to satisfy that, and so we can take the difference of these two equations to get y equals z as required. And so this is not a function, but this one is a function. Okay, let's stop there.